Hi everyone, welcome back and welcome to the light and atoms topic. So in this topic we're going to start with a bit of an intro about waves, talk about the spectrum of light and go from there. So some of this for this lesson and the next lesson may be a little bit of revision, maybe stuff you already know, but it's really important background for what we're about to cover. So firstly, the science understanding, this is from the SACE outline, this is what we're going to cover today. So let's look at the electromagnetic characteristics a bit more. Electromagnetic waves are a form of radiant energy. Radiant energy refers to the energy of the electromagnetic wave. There is an electrical component to these waves and a magnetic component, which is why we call it the electromagnetic wave or the electromagnetic spectrum. In a lot of the course we'll refer to it as the EM wave or the EM spectrum for short, just because electromagnetic is really hard to say. So that's why it's called that. It has an electrical part and a magnetic part. I'm glad you asked. Why does it have these two? In the subtopics from before, we saw that a stationary charge produces a stationary electric field. If we have an oscillating charge that's moving around, it produces an oscillating electric field. Then in the slightly later topic in 2.3, we saw that if we move that charge, it produces a magnetic field that is perpendicular to the movement of the charge. So remember, a moving current or a moving charge produces a magnetic field. That's really important because that's exactly why we have this electromagnetic wave effect. So this was in addition to the electric field created with a charge. So that moving charge has an electric field. By moving it around, it produces a perpendicular magnetic field. And this is starting to sound a lot like what a wave does. James Clerk Maxwell was a Scottish mathematician and physicist. In 1864, he introduced his theory for electromagnetic radiation. This theory is sometimes referred to as the wave model for light and is based on the idea that an oscillating electric field produces an oscillating magnetic field, and conversely, an oscillating magnetic field produces an oscillating electric field. So when a charge is forced to oscillate, it produces an electromagnetic wave that consists of this oscillating electric and this oscillating magnetic field. The two fields oscillate at right angles to each other and to the direction of wave propagation, which is just the direction they're traveling. So that's an important word. When we talk about direction of propagation, it's just which way is the wave moving, like where is it traveling to. By definition, the electromagnetic waves are transverse waves, which hopefully from last year you remember what it means to be a transverse wave, and they travel with a speed of 3 times 10 to the 8 meters per second in a vacuum, which funnily enough is the speed of light. When moving through a vacuum or air, the electromagnetic wave consists of oscillating, mutually perpendicular electric and magnetic fields. That is a very important definition. That's what they want you to be able to explain. They're oscillating, mutually perpendicular electric and magnetic fields. So all that means is oscillating, they're going up and down. They're mutually perpendicular, just means they're perpendicular to each other. One is coming, say, out of the screen, the other is going up and down. They're mutually perpendicular. And they're made up of an electric and a magnetic component. That's all it means. Electromagnetic waves are transverse waves, and they're made up of this mutually perpendicular oscillating electric and magnetic field. So that's the full definition of what an electromagnetic field is. So we mentioned that the fields propagate each other. The plane of polarization is the plane of the electric field. So anytime we're talking about polarization, which is coming up, we're talking about the electric field plane. So whichever direction the electric field is traveling, that is the plane of polarization. So just to recap, for the EM spectrum, the electromagnetic waves and the electromagnetic spectrum were covered last year. The frequency is the same as the frequency of an oscillating charge that produces that wave, because that's what defines the frequency. So later on we'll talk about a charge moving up and down. That is the frequency that generates the wave effect. The frequency of that oscillation is obviously, or has to be, the frequency of the wave, because that's where it comes from, and it's not dampened by anything. Therefore, the frequency of the oscillation will determine the type of electromagnetic wave. Because when we talk about a frequency, as you can see in the spectrum guide down here, the frequency is what affects what kind of wave. Whether we have gamma, ultraviolet, etc., that's all based on frequencies. So the faster I oscillate whatever that thing is, the higher or lower it becomes on the spectrum based on that frequency. We will use the wave equation a fair bit, and this will pop up a few more times in the next lesson or two, but that's that v equals f lambda. So the speed of the wave is equal to the frequency times its wavelength. This equation tells us that there's a directly proportional relationship between frequency and the wavelength. In this case, if we want to conserve energy, so I've got a certain amount of energy, if I increase one of those with the same amount of energy, the other must decrease. So if I look at this piece here, if I've only got a set amount of energy, but I suddenly increase frequency, the wavelength has to drop to offset that number mathematically. And that's that conservation. So there's an inversely proportional relationship between those two. So that should have been inversely proportional, not directly proportional. There's a directly proportional between the velocity and frequency and wavelength, but inversely between these two. So this is why a high frequency wave has a small wavelength, and conversely a low frequency wave has a large wavelength. So it's all because of the V equals F lambda formula. So this is a representation of the full electromagnetic spectrum. This is all the possible frequencies that we can have, or at least that we know of, all the way down from your radio waves up to your gamma rays. And there's a list of some basic examples of things that use those kind of spectrums, and we'll talk about that in a little bit more detail. So let's look at radio waves. We're familiar with the concept of AM and FM radio. AM, maybe not so much, maybe your parents use it a little bit more, and shortwave radios. FM waves carry the picture portion for your television, for most TVs, and the sound is mostly carried by the AM. This is probably a little bit different now with your digital TV systems, but in the typical TV system, FM was your picture and AM was your sound. When we go to microwaves, it's a high energy radio wave. We use them in communication as well as conventional microwave for cooking, which is what most people think of. They reflect off certain surfaces and they're absorbed by others. So we can use this attribute quite well to bounce it off objects and absorb it by others, which is going to heat it up, for example, in the microwave. So infrared is the next piece that we're looking at. Infrared waves are slightly longer than the visible red light, and they're used by certain types of cameras to show heat. So one of the most common that we know about is like thermal imaging, which is a type of infrared. We also use it a lot in astronomy and things like that, looking at different auroras, nebulas, and stellar objects in the infrared spectrum. They can also use it for forest fires and things like that to identify like hotspots and where it's spreading and things like that. Visible light is obviously the most common aspect of the EM spectrum. Each color, the Roy G. Biv, the red, orange, yellow, blue, green, blue, indigo, and violet, have different frequencies. So that's really the only difference between a color is its frequency band. Red and green and blue are the primary colors, and we can combine these three colors to make everything else. So this is with like lenses, not talking about like paint. Mixing paint's very different, but red, green, and blue we can mix and create any other color in the spectrum. Ultraviolet is our next one. So ultraviolet is the main source of sun rays that come in. They can be used to destroy bacteria and viruses in a good way as well as a bad way, and they also cause what we know as sunburn and skin cancer. So it can have both effects. We use UV to sterilize water and things like that. We have very powerful UV lights that are shone through tubes, and the water runs through it, and the UV basically kills everything that lives inside that. We use UV a lot again in astronomy. It's a great way to observe the sun in UV. We can look at things like the moon, again looking at auroras, and a whole range of things. So there's different spectrums that we can view, especially for astronomy based stuff. We can see a lot more than we would see in the visible spectrum. X-rays, for those of you that have had your teeth or your bones x-rayed, you're familiar with the concept. Again, it's a whole range of uses. We can use it to identify certain things. We'll cover x-rays in a lot more detail later on. We've actually got a whole topic on what we use x-rays for, how they're made, things like that. Then we've got gamma rays. So a lot of radioactive material and nuclear reactions give off gamma rays. They damage living cells and are sometimes used to destroy cancer. So again, it's always a pro and a con. Like, it's bad in the sense of it can destroy living cells and cause a lot of damage, but we can also use that effect to destroy specific cells like cancers and things like that. And again, gamma sources are a big thing for things like supernovas and other astronomy observations.
Tell me pretty lies, look me in the face, tell me that you love me, even if it's fake.